Cool, thanks. Thanks very much to the organisers for having me. I'm a research fellow in Mike Tildersley's lab at the University of Probert in the UK, and this is very much a collaborative piece of work between the US, the UK, and researchers in Japan. And I'd particularly like to point out Mike Tildersley, who's run all the simulation results for this, and Chris Jewell, who you've just heard from, who ran the parameter estimation work, and particularly our colleagues in Miyazaki and Satoshi Sekiguchi and Yoshitaka Goto for help with the data. At the heart of the problem that I'm going to talk about is this recognition that in these sequential decision-making problems, disease control problems, we have this relationship between information accrual and capitalizing upon that information by taking action. So when an outbreak occurs and we gather more information, we can make more informed decisions with more information. But in an emergency situation, we don't have the luxury to just sort of sit around and wait for information to occur, to come in. Policymakers have to make decisions in the face of this uncertainty, so we have to act. So we wanted to look at what was the ramifications of that process of information accrual on how does that impact changing control recommendations through time when we're using epidemiological models to generate control recommendations. And we applied this methodology in two case studies, two contrasting case studies, the UK outbreak in 2001 and the outbreak in Miyazaki in 2010. And these were contrasting in a number of ways. The severity in the UK outbreak, there were over 2,000 infected premises, whereas in Miyazaki there were 290 roughly infected premises. The distribution of infected cases at the time of confirmation in the UK, there were multiple foci of infection, whereas in Miyazaki there was a single focus. And the control actions that were applied were very different. In the UK it was only culling, whereas in Miyazaki vaccination, as you've heard, was implemented. So our approach to sort of looking at this question of information accrual and how that impacts control recommendations was to retrospectively look at both of these outbreaks and parameterize a model at weeks throughout both of these outbreaks, and then do forward projections from those weeks under a range of different control strategies. And so this is the case distribution of infected and culled cases in the UK outbreak. 1 week after the first confirmed case on the 26th of February, we parameterized the model and then fed that into a forward simulation model and made forward projections under a range of different control strategies. And the projections that we get are conditional on our parameter estimates at that point in time, only using the data that we have after 1 week after the first confirmed case. And they're also conditional upon the state of the outbreak at that point in time. And what I mean by the state of the outbreak is this distribution of the confirmed infected cases and the susceptible premises, those locations of them. But using the method that Chris has just outlined, we can do better than that. We can estimate these undetected infections, or these so-called occult infections. So at each point in time, we would also have a distribution of this spatial distribution of where we think these undetected infections occur. And you can think about this as sort of a vector of infection times of those undetected infections. So we're not assuming a fixed time point from infection to confirmation. So the projections that we get at each point in time are conditional on our parameter estimates and the state of the outbreak, where that is both our known infected cases and these inferred infected cases. So at each week throughout the outbreak, we can parameterize the model using the methods that Chris has outlined, and then we can do forward projections under a range of different control strategies. And we can do that on the second week and the third week and so on. And these are what I'm going to term projections based on accrued information, because they're only using information up until that week in question. So it's as good as we could have done with the information at hand. And we want to look at, so in summary, just at each week what we were doing, we were updating parameter estimates with new data using Markov chain Monte Carlo methods that Chris has outlined. It was a species-specific herd level infection model. And at each point in time then we have this joint distribution of parameter estimates. Each point in that is a parameter estimate of 16 parameters that we have, and also associated with that parameter estimate is this estimate of the infection time of these undetected infections. This is conditional also on the true outbreak up until that week. We're not assuming that control happened in any different way than what actually occurred. And then at each week as well, we're taking those parameter estimates and we're doing forward projections under a range of different control strategies based upon the spatial distribution of these confirmed infecteds and also the undetected infecteds that we've estimated. And this is outlined in papers by Matt Kelling and Mike Tilsley. We wanted to isolate the effect of information accrual, so we were comparing these forward projections that we made based only on the information that we had at that point in time with projections that we would get using parameter estimates estimated using all the data from the whole outbreak. So on 24th of, this is just for the UK outbreak, these dates are obviously different in Miyazaki, but on the 24th of December we made another estimate of the infection parameters. And then going back for each week throughout the UK outbreak, we made forward projections using the state of the outbreak at that point in time, but using parameters from the very end of the outbreak. So we can compare forward projections between these two cases based on sort of the best data that we had at that point in time and sort of the best that we could do if we had all the data from the outbreak. I'm not going to go into a huge amount of detail about the model. This is just to illustrate the uncertainty associated with the parameter estimates. So we could summarize, as a sort of proxy for R0, we could summarize the risk of onward spread using the parameters that we had at each week throughout the outbreak. So this is for the UK outbreak. It shows the first 5 weeks since the first confirmed case and the last week, so week 28. And all I wanted to point out is just that our risk of onward transmission is decreasing through time and our uncertainty associated with infection parameters is decreasing through time as well. We have estimates of these undetected infected premises. This is summarised at the county level for the UK because there's just so many farms in the UK, and this is showing the expected number of undetected infected premises for weeks 2 and weeks 3 in the UK outbreak, both estimated at that point in question, so accrued knowledge, and using all the data. And I just want to point out that our estimates of where these undetected infections are changing through time, and they're becoming more resolved through time, focusing on where the actual infection is as more information is garnered. And similarly, we can do this for the Japan outbreak as well, and we get similar results. Here I'm showing, instead of showing it grouped at the county level, I'm showing individual farms. So we're looking at the actual probability of that farm being an infected premise. But what do these mean in terms of changes in recommended control actions? So I'm going to show you results from the forward projections, and bear with me, these are big plots, but there's three panels. The top one shows projections of outbreak size here in total colours. So it shows the summary of 2,000 simulations under a range of different control actions. The second shows the ranking of those control actions according to the median in the top panel. And the third one shows the proportion of times that any one control action would be chosen as optimal if we took a bootstrap sample from the top, one sample from each of those distributions in the top panel and compared them. So the bottom panel sort of gives you an idea of how much of an overlap there is between the different distributions. Along the x-axis will be time, so I'll show you weeks since the first confirmed case in both cases. We had 6 or 7 different control strategies, different between the UK and Japan. Culling of infected premises in light grey, and culling of infected premises in dangerous contacts in dark grey, which is the minimum under European and Japanese law. The culling in purple, culling of infected premises, dangerous contacts and contiguous premises, most similar to what was done in the UK outbreak. Ring culling at 3 kilometres and 10 kilometres, and ring vaccination at 3 kilometres and 10 kilometres. So we can look at what our control recommendations would be at weeks. I haven't shown the whole outbreak here because there'd be so much data that you wouldn't be able to see anything. But these are the first 5 weeks and then the final week at week 28 for the UK outbreak. So just broadly speaking, we can see that our projections are changing through time, but also our rankings of control actions are changing through time. What we're choosing as the optimal control action is changing. We want to compare these with what would our projections be had we had all the data. So beside these, we have the projections based on the complete knowledge. So we can see that early on our projections, on the left-hand side, these are projections based on only having the data at that week in question, and beside it are the projections that we would have if we had all the data. So we can see early on the projections really overestimate the outbreak severity in this case. But if we look at the rankings of controls, they're resolved relatively early on. So even though the absolute size of these projections are not in line with what we would have had we had all the data, the relative performance of the control actions within our model is still reasonably robust. We can see it at about week 3, so from week 2 to week 3, we see this large resolution in the relative performance of the different control actions in the accrued knowledge case. And if we look back at our distribution of undetected infected premises, we can see what's driving this. Is we've got sort of this resolution of where the infected understanding of where these undetected infected premises are. We're quite sure that they're not occurring in the north areas of Scotland anymore. And this is providing resolution in terms of what's the recommended control action. So it's this underlying spatial distribution of undetected premises in the state of the outbreak that's changing through time that's really driving this change in the recommended control action. And for the outbreak in Japan, we can see the first 5 weeks and then the final week, the recommended control actions didn't change terribly much, even though we had the same sort of situation where the projections were uncertain at the start of the outbreak. The interesting thing in the outbreak in Miyazaki is that we got, I'm not sure if you can see it on this slide, but we had quite a lot of cases where there were large bimodal distributions where a second focus of infection occurred and we had some of these large outbreaks occurring. But this was never enough to change the recommended control action in the Japanese, in the forward simulations for Japan. So in summary, the results that we have sort of show that we had these large, this sort of uncertainty at the start of the outbreak associated with the where the infection was and how the infection was spreading in our parameter values. But despite the poor estimates and all this uncertainty, the relative rankings of the controls that the relative performance of the different controls that we, under the forward simulations, were resolved reasonably early on. We saw that the optimal action was strongly influenced by this underlying distribution of the infected premises, and just sort of illustrates the importance of continual updating of both the evaluation of our different control strategies, but not only that, where we think these infected premises are. As Chris mentioned, in feeding in information where we know infected premises are not, where we have confirmed negative cases, this is going to be useful. And I wanted to point out that the estimation of these of our infection parameters and the undetected infected cases is an intertwined process. We can't do one without the other, so it needs to be a complete analysis. And finally, because our control, we can see that the relative performance of controls was strongly influenced by the state of the underlying infected premises. Really, this sort of, generally speaking, this sort of illustrates that we need to be generating control that adapts to the specific outbreak at hand. And this is something we've been looking at, taking methods from the artificial intelligence literature and applying methods under the sort of umbrella of what's called reinforcement learning, and generating control strategies that can adapt as an outbreak unfolds. And if that's, I don't have time to speak about that today, but if anyone's interested in talking about that, then please say hello. And with that, I'd like to say thanks.
Given the time, there's room for 1 or 2 questions for both of the presentations. Who can I give the floor? Either everyone is very impressed or no.
Any Japanese in the room? No? No, I would have liked to hear their opinion. that they vaccinated too late and in the wrong place. Did you have any feedback on that from Japan? That conclusion?
I think that's been reported straight about how many states. It's very much a work in progress, isn't it, Chris?
It's broadly consistent with the sort of field team post-hoc analysis of the outbreak, particularly the Morogo paper. Thank you. Yeah, it's broadly consistent with the field team analysis of the outbreak and papers that have been published on it. So we're actually fairly confident that the model is picking up something that's real and already recognised.
Okay, thank you. Given the time, we are running out of time, so I was reminded. So we quickly go to the last